All right, let's jump right into part 2 of our binary aperiodicity explainer. Today, we're tearing down the physical illusion of binary. We are going to take a really fascinating journey down into the literal atomic core of your devices to see what's actually happening inside the silicon that runs our world. And I got to tell you, it is wildly different from what we've all been taught to imagine. So let's kick things off with a deceptively simple question, just to challenge our assumptions a bit. Where do the ones and zeros in your computer actually live? Seriously, take a second to think about that. When you save a file or send an email or, train an AI model, where are those binary digits physically residing? Because the answer is probably going to completely shatter how you look at computation from here on out. But hey, before we shrink down and go inside the machine, let's start up here in the human realm. Take a look at the Berne Convention. It's the oldest, most comprehensive international copyright treaty in the world. It basically exists to fiercely protect literary and artistic works. And it's a huge testament to how aggressively we humans protect our text, our art, and our symbols. And we protect these symbols so fiercely because they contain meaning, they contain authorship, and what the law literally calls moral rights. These are rights that actually protect an author's honor and reputation. We view a creative work as an absolute extension of its creator's identity, right? We intuitively know that symbols and text aren't just arbitrary squiggles on a page. They carry the heavy, significant weight of human intent. So the big takeaway here is that human symbolic cognition serves as our own primary operating system. Let's just call it OS alpha. It's an operating system built entirely on associative thought, intuition, and meaning. You and I, we don't think like rigid, step-by-step algorithms. We think in these massive, messy webs of interconnected concepts. Our entire reality is driven by how we interpret symbols. Which begs the question, how on earth do we get a cold, unthinking piece of metal to process our highly associative human thoughts? Well, we build a semiotic bridge. We start by writing expressive text, code, using our OS alpha. Then, we run that text through formal compilers, things like CompSert, which mathematically strip away all of that fuzzy human ambiguity. Finally, that super rigid instruction set is mapped directly onto the hardware. Basically, text is the universal deterministic interface bridging our minds to the machine. Okay, now here's where we completely pull the rug out from under you. Inside the actual machine, there is absolutely no text, there are no semantics, and there are literally no ones and zeros. There's this fantastic quote that just hits the nail on the head. For computers, it's raw electrical signals all the way. Input, processing, output. No symbols for computers. All of that beautiful human meaning, it completely stops at your screen. And that perfectly illustrates the stark contrast between the warmth of our human meaning and the cold, unthinking physical reality of silicon logic gates. Up in our minds, we've got OS alpha, symbols, semantics, all that good stuff. But down inside the physical arithmetic logic unit, you are not going to find some microscopic physical 1 or 0 floating around. No way. You will only find clocked voltage levels, semiconductor switch states, and transient electrical charges just rushing through copper wires. That is the whole shebang. We really have to internalize that the word machine is just a metaphor. And binary? It's just an illusion we all agreed upon. It's basically a polite fiction. A human-imposed constraint we use to make those chaotic, raw physical transient charges somewhat manageable. We just arbitrarily decide, okay, a high voltage represents our concept of a 1, and a low voltage represents our concept of a 0. And get this, when the physical reality of the silicon naturally deviates from those imaginary boundaries, we throw our hands up and call it a hardware glitch. But the universe didn't glitch. It's literally just physics being physics. It is only a glitch relative to our totally made-up binary constraints. So, forcing a physical object to act like a fake binary Turing machine has actually created a massive real-world problem for us today. Let's look at the consequence of all this, the von Neumann bottleneck. Here's the deal. Standard computer architecture separates the memory from the processing unit, and it connects them with a physical wire called a bus. But because we absolutely insist on treating continuous analog voltages as these discrete digital blocks of data, we have to constantly shuttle these fake binary digits back and forth across that wire. And in modern AI, things are so interconnected that your ultra-fast processors actually end up just sitting there idle, twiddling their thumbs, waiting for the data to arrive. The physical charging and discharging of those copper wires just to move this data around, it consumes a staggering 90% of the total energy budget during AI runtime. 90%. The actual math only takes about 10%. It's wildly inefficient. When you compare our standard, highly inefficient GPUs with a true physical solution, the difference is just night and day. Standard von Neumann architecture forces this incredibly high data movement, which leads to severe memory wall latency and extreme thermal dissipation issues, meaning we are literally burning massive amounts of energy. But look at the alternative here, analog in-memory computing, or analog IMC. It boasts zero data movement, none. It executes math not by using fake digital logic gates, but by relying purely on the sheer existence of Ohm's and Kirchhoff's physical laws. So, to fix this crippling bottleneck, we can't just keep trying to optimize a binary illusion. We have to start returning to analog physics. Which brings us right to in-memory analog computing. This architecture just throws the binary illusion right out the window. It completely merges data storage and computation into the exact same physical substrate. Meaning, data never has to travel across some shared bus to a remote CPU. The calculation happens exactly where the data already sits. So how does this black magic actually work? Well, it calculates instantly just by existing within the laws of physics. You simply apply a voltage, which represents your input, to a crossbar array, and instantly the actual physical resistance of the material inherently multiplies that voltage via Ohm's law. Then, those individual currents naturally flow together, literally summing themselves up along the wire thanks to Kirchhoff's current law. The hardware isn't processing rigid instructions to do math. The physical reality, the electricity passing through the material, is the math. And it all happens in a single instantaneous analog clock cycle. Now, just to show you how real and honestly how close this all is, let's look at a scalable hardware breakthrough that recently came out of the University of Michigan. They developed something called the Bismuth Selenide memristor. And if you're wondering, a memristor is basically just a resistor that actually remembers the electrical state it was last in. Let's check out the anatomy of this thing. They built a vertical stack using gold, bismuth selenide, and titanium. When they apply a voltage to it, tiny finger-like gold filaments actually physically grow and extend upwards inside the layer. And because they can extend and retract without ever fully bridging the gap to the top electrode, the device achieves this incredibly smooth, continuous analog tuning. It's not just rigidly flipping an on or off binary switch anymore. It's dynamically adjusting. It's actually a whole lot like how biological synapses in your own brain physically strengthen or weaken. The researchers actually tested this out by integrating these memristors into a fully all-hardware network to control a physical balance lever. And because they totally bypass the need to constantly convert signals back and forth into that digital binary illusion, the system calculated the perfect angle using an incredibly tiny 7 microwatts of power. Guys, that is just 7 millionths of a watt. To put that into perspective, a single highly efficient household LED light bulb uses about 8 to 12 entire watts. By ditching the binary illusion, they bypass the massive energy drain completely. I want to leave you with this final thought for today's explainer. We started out by looking at how fiercely we humans protect our meaningful symbols, right? And then we went way down into the physical core of the machine, only to find that absolutely none of those symbols actually exist down there. It is literally just raw electricity all the way down, blindly guided by physical laws. So if computation at its core is entirely devoid of inherent semantics, are all these vast digital worlds, these huge AI models, and the software environments we create, are they really just reflections of our own human operating system? Is the machine truly learning, or is it really just holding up a highly complex electrical mirror to our own human associative thoughts? It's definitely something to chew on. Until next time, keep questioning the illusions around you.